Caracanhas from the University of Sao Paulo with the campus Carlos. Monica, we are very much looking forward to your presentation. Please go ahead.
Okay, thank you very much, Axel. I would like to start thanking the organizer for inviting me to this talk. Apologize for not be attending presentially. Then this presentation, I would like to talk a little bit about superfluid vortex dynamics and curved surface. That is a work that I developed with Let's go to the overview of the talk. Start with the introduction. Bose-Einstein condensate in gases. Then I talk a little bit about the bubble. Then I will describe a little bit about the superfluidity, velocity field in a case of a 2D plane, superfluid fumes in 2D. And go on to the interest that will be the superfluid fumes on the surface. Here, other that is basically the last topic of my talk. I generalize not just the sphere, but all axial axis symmetrically compact surface. And then the conclusion. Well, start then with the introduction. Since the creation of Bose-Einstein condensate in 1995, ultra-cold gases have to as a platform to simulate condensed matter models. For example, we have fermionic gases, degenerate gases trapped in optical traps, light, optical traps. And this system can, for example, simulate the electrons in crystalline structures of solids. And also with these ultra-cold gases, we can explore exotic quantum phases, that is totally new regime that is not reached in the usual condensed matter system. Also, these quantum gases have the big advantage of having high control. We have a big control of this experimentally in this system. Also, the atomic states, the internal and external degrees of freedom, can be controlled very well by using optical and magnetic. Here's some example of these techniques. We have these is uniform magnetic fields. You can tune the atomic interaction by using. You can change it. Also, if you could use laser beams to produce steering the sample and also information in the traps, this can produce the vortex and also collective modes. You can change the confinement system, and the condensate can go from a concave trap to a cigarette. Also produce that logical potential. And with this control of the trap, you can change.
Mônica, nós cortando muito o teu som, eu não sei se era melhor você entrar e sair de novo. O som tá muito cortado.
Okay, Arnaldo. Better log off, then okay, I'll try to do that.
I think it's better you get out and try another time, please.
Okay, I will try.
Estão falando que o microfone, você tem que usar o microfone do computador, estão falando.
Can you hear me?
Yes.
Is better now, Arnaldo?
Much better.
Okay, then this is the microphone, the problem, not the connection, because the sign here is very good. Okay, sorry about that. Can I go on?
Yes.
Okay, I think I go on. Just return to here. Okay. Okay, then I stop here. I explain about the traps and how you can control the dimensionality of the system. Then you can go to effective 1D or 2D system, just controlling the magnetic and or optical trap. And also change the topology of the system. try to create ring rotation and also the bubble trap. And besides all this control, you have how to probe your sample very well in these classes. And you can use fluorescence or optical absorption to obtain some number, density, and also some techniques, the phase contrast image to catch information about the phase of the macroscopic. Then to summarize, this is an ideal system for studying superfluid dynamics. And here, I will try to show how to use them and use the system vortex dynamics on curvative surface. The main topic. Let's summarize a little bit what's bubble traps. I think you have already had a very nice talk in Nathan Luther about these traps. Just a brief description. Propose of creating these thin shell traps. Bubble, given by originating about rest potential that can be generated by superfluid static magnetic fields, usual quick traps, the radio frequency fields that are coupling. And this radio frequency technique is basically the same one that you use doing evaporative cooling. And this is the ingredients to produce those magnetic fields. Trap your in a bubble shape. Also, I'd like to mention here, this is the pioneer works that summarize how developed. I'd like to show in the Earth, we have the problematic thing that you have the gravitational fields, then you have two additional put magnetic gradient fields to compensate the gravity. An alternative way to generate these traps, the influence of gravity, was made in the NASA code laboratory, and there they recently produced three-dimensional BC with no gravity. Very important events, reach very ultra cold temperature there, avoid the sagging problem, the location of the minimum. And also to produce more uniform filling bubble trap without the of course, you still have some inhomogeneities, even this case, because you have some problem with some homogeneity in the magnetic field trap. But one of the aims of these experiments was creating a visualized vortex in particular geometry. Motivation. Have studied this. Create because of the finite temperature. Now I go to my first part, that is describe the velocity field of the superfluid. We know that the quantized vortex was a signature of superfluidity in this whole. Was observed in helium and atomic BCs. Basically, this is a manifestation of angular momentum. The systems are described by scalar complex by the modulus T, and this phase is connected with the velocity of the flow of the proportional to the gradient of this field. And just because of the velocity has dependence with the gradient of phase, we already conclude that this will be a rotational field, the rotational of zero, except in some singular points that we characterize our vortex. Then you have how to define the quantity circulation to get a closed contour around a vortex. Then you characterize the equation by kappa here, basically the integral of the velocity assume that this form for the you already see that the kappa is basically be proportional to the variation of the phase of the wave function. And you know that in a closed contour, the phase would not be changed. Then we have to go to the integer number of 2 pi to guarantee the single value of the wave function. And there is that the phase has to be quantized, delta phi, quantizing integer number of 2 pi, and then the circulation will also be quantized, but here the unit of circulation, the Planck constant divided by the atomic mass. And me, here is the integer number, quantized circulation. Okay, then I would like to tell here that for this low temperature system, you have no dissipation. In this scenario, you can describe your superfluid as being an ideal fluid, that you obey this classical aerodynamic equation. Then, what is the ideal fluid? Besides being rotational, also incompressible. The divergence of V equals to 0 to 2 factors that define superfluid as ideal. Just because of this incompressible condition, you can also represent your velocity field in terms of another scalar potential that I call here as a string function. So before that you have to define the velocity with the gradient of space, v, but here we have an alternative description that basically is the rotational or the gradient of so e. Here I function, here it just represents the normal to the plane. Remember, I was describing the well, this quantized condition for the circulation gives us that the vorticity has delta function, where our node is the position of the vortex. This basically you can count the expression using that expression for kappa, the circulation, and the Stokes theorem, where we have a circulation around the closed contour. You go for the integral in a surface that you are confining that contour of this rotational. And then you see that you have to guarantee the quantized circulation, you have to be singular in the position of the vortex. Then in this expression, we can replace the velocity field function, and you see that the string function will satisfy a Poisson equation, where the vortex is basically the source. Familiar, us that from electrostatic we have electric fields, where the source is the charge. This is a scenario shows that why it's advantageous for us to use string function as a characterization of vortex velocity. We have a direct connection with vorticity. Okay, and I conclude. You have the velocity, this true description of the velocity in terms of the gradient of v or the other e. Format here looks like that vector potential. Well, this equation is basically the Cauchy-Riemann equation for the relates for a complex potential. Plus components is scalar potential. This can give us a general complex potential. It's the combination of E plus I P. The imaginary part is giving the phase V, where the real part function, and Z being the coordinating convenient description. So you see that you have look at the derivative of F with respect to V, we cover consider the components of the flow. The hydrodynamic flow velocity variation. An important relation. Okay, just an example of application of transportation. Then you consider a single vortex discharging Q node and position in the complex plane, position in P node. Here you have the charge times the logarithm of V minus V node. And using the derivative with respect to V, you already get this dynamic flow, pressure of charge, and this is the unit. Okay, let's then consider a case where the vortex is at the origin coordinate. Have a positive unity plus one. And you already recover the pressure. Have this axisymmetry, goes in the inversion of the distance of the vortex. Here I try to represent the velocity field here. The magnitude of the arrows is decreasing as you are far away from the singularity. And have the phase here represent that is the radial, the uniform in the radial direction. You can radial contour, perpendicular to this radial contours, you have this free function in the contour that is parallel to the flow, velocity flow. Characterize both rotation and well, this is just for velocity of a single vortex. Now we want to know the dynamics of the vortex when they are subject to the interaction with all other vortices in your system. Then, for example, for any V vortex, arbitrary positions are there. You can calculate the total string function of the sum of the individual vortex, where just remember the string function is the real part of that complex potential. Just the logarithm of the module, R, the position of interest, and Rj, the position. Okay, then use that expression for the velocity. You already get formula for the arbitrary position R in the plane. But how about the velocity of a specific vortex charge? For example, the vortex K. In this case, you have to catch this velocity Q in the exactly position of the vortex. Velocity of it. The goal is the flow. You have to consider the flow of all of the vortices in the position of this particular one to get his velocity. This is the formula above that is getting for R going to RT. Basically, you see that the velocity of vortex K will be all the string function of the other vortex K here in the position of T. Of course, you also get out the takeoff self-flow, that one that the vortex K produces history. Singular. That's the well, until now I just described the just summarize and remember you about the how about you have just not a plain superfluid field, but a superfluid that has this spherical shape. Well, let's just start mention that to have this surface. Make here a contour. Then you have to define this contour just share this region in region 1 and 2. Not how to call here interior or out or external, just 1 and 2. And if you consider in relation to the region 1, sense of circulation, for the region 2, circulation, you have opposite sense. Then if you have, for example, a constant line of phase going from this source vortex, they have to reconverge somewhere in the outside region, in the second region. The reason that, for example, in this kind of surface, the more simple configuration of vortex that you have is a dipole vortex. And that is the sum of all the charge but there have to be 0 always. And you can see here we have a positive and negative one. White show you the contours of constant phase. You have to reconverge positive, converging position that is negative one. Here in black, show you the corresponding string function contour. So this is then the opportunity. You have to determine how you calculate these functions over the and the method to do this is the graphic projection onto a complex plane. Here on the complex plane, then you will determine the starting in the complex plane that you know how to do, and then you use this projection to convert again to the. Before I explain better this method, I would like to consider some assumptions of the model. I've already told you one, compressive superfluid. Also isotropic S-wave interaction between the atoms, repulsive, that gives us uniform thickness, film, and density. Consider also that the fluidity of this film is less than coherence length. To avoid this line bending, then you can treat our vortex like point vortex model, and without thinking about things. And the vortices are characterized by a constant form. The important thing. Okay, let's go then for the spectrum. Basically, we are considered here a slice, a sphere. And above it, you have a plane. That's the complex plane that you do the projection. You see here the coordinate in the plane, in the form, O times exponential. And you see for this specific slice, you have a particular P, a point P on the sphere, and will correspond to a point what's the name? Okay, both have the same P, coordinate P, but here you can show in this figure how to relate the distance, radial distance in the complex plane. This angle theta in this tangent of theta by 2, O divided by 2r, r being the radius of your. Then you have here how to relate the coordinate of the complex plane with that one in this sphere. Same. Use this coordination this sphere, starting with the complex quotation that I showed you how to determine. Let's go then for a simple example, more simple computations. That's both here. And you saw already that the potential basically by the fraction, which is the potential for the positive and one for the negative. Basically the ratio and of course this is the coordinate of the complex plane. How we use the stereographic projection that go to the potential in the you just replace coordinate z by 2r times the tangent of theta and the connection angle phi. Basically, this is the formula for the semi-potential for the whole system in this field. Now you take the real part of this, and then you get the string function. Here, omega here is deviation for theta in p coordinates. Again, this is basically the string function of the positive minus the string function of the negative component. This is the expression of the arbitrary charge J in a position omega on the P, dependence of the coordinates theta and P, the coordinates of the vortex, theta J and P. And a group is argument of the logarithm as the expression here times the sino of this gamma J, where gamma J is basically the angle between the curving the sphere and the position of the angular aperture. This quantity here also can be associated with the chordal distance. Here, it's basically the distance between the straight line that connects these 2 points, not passing through the surface, just are connecting these 2 points. Then you see that the string function is logarithmical of chordal distance. Okay, and how about the dynamics? Just determine the string function and the surface, and then for get the dynamic, you just get to formula. Take it again, these are in the position of a vortex that you are interested in. For example, this is a general case, but the positive one, positive one. And you have to know the string function that the negative one produce over the position. Vortex. You take the gradient and the rotation. Here is the expression for the function of the minus time vortex. And give the logarithm of the distance, angular distance between both, divided by 2. And here you are considered gamma, since you consider that both start at the same angle. You can do the sphere, you can literally use this symmetrical. And you just have velocity field of plus vortex, velocity of minus vortex. That's basically this cotangent of the difference between both the phi direction. Consider equidistant vortex on the equator of the sphere, more symmetric. And you have this velocity field proportional to the tangent of the angle theta. Theta is the angle that the positive vortex takes with the north pole. Well, here then that expression can have 2 limits. Here I have already told you the fact that the vortex dipole moves synchrony in uniform direction and keeping the separation fixed. That is proportional to the that means that if theta goes to 0, that is, you have one vortex in the north pole, other one the south pole, the velocity goes to 0. The static. On the other hand, if the theta goes to pi over 2, both vortices are meeting together in the equator, then we expect that have a divergence. Also, the limits that are very, very close, velocity of the dipole is that one that you expect for the planar configuration. In R delta E, almost linear distance. Here is an example of these orbits. Here is a more general, not exactly symmetry around the equator, but you see, you always have this moving a constant angular separation, keeping sort of distance constant, in parallel to the greatest poles. So the equator, the main sequence can be defined as the middle point of the always in the direction parallel. So here is not a C anymore, it has a combination of theta, but it's always parallel to this secting. Okay. Yeah, I told you about more simple interpretation, but you can extend and still treat more complicated one. You have here 2 plus vortex and 2 minus, and the sum of all these charges have to be 0, to guarantee the neutrality. Have some simple metric configuration that you can still do some analytical tools to predict the orbit. That I will try to include here. Consider 4 vortices. They are all start with the same plane. The configuration have the 2 plus sign vortex in the upper part of the sphere and the 2 minus sign in the subpart. You assume you calculate the string function and derive the velocity field, you see that all the 4 charge vortices have the same velocity field, and all will rotate together in a counterclockwise sense around this direction. Have a film here. This is the movement that you have. Not wrong, the black and red is the positive charge. No, sorry, this is on the positive and this is on the charge. Just circling around the x. In some cases, that is the limit of this. You consider this theta very small. Then you have the 2 positive and negative precessing around the poles. Looks like the planar case. You have this heat that sorry, is the first one. One. They're seeking orbitine warp, the poles. Another situation when you put the minus sign and plus sign very close to each other in the equator, then you get the 2 independent dipoles that are also make this precession in the same sense, the parallel to the equator. Limit case. How about you exchange that same configuration for planar one, but we extend the position of the positive and negative charge for it. Then you have plus minus above and minus plus. In this case, you have a particular interesting case that then theta is equal to 4. Guarantee that you have the same angular distance between all the vortices. Then you got a stationary configuration. All the velocity fields are make some perturbations around the stationary points. You see that the vortex start precessing around these points, like a equilibrium configuration. So after you have round pi over 4. Well, we'll also make some question about the area of these orbits. I'd like to talk a little bit about another configuration, limit configuration. Here, that angle of theta here, very small. For example, you consider start with the difference in the north, the other one in the subpole. What will happen is that in opposite of the first configuration, they are move on in opposite sense. They meet together in the equator. Then they will exchange partners and move on around the equator. After half period, they are meet again, exchange partner, and move on the orbit, over 2 degrees. They go here from north to south. They are here from east to west. You can also analytically predict the period of this orbit. Know the distance, the velocity of the star, the very small dipole, the inertial of the dipole, and the distance traveling time without the period. And just the last one is now is not coplanar anymore. You consider a tetraedic configuration. And this is also a stationary one. Also, all the velocity. In opposite to the other case, here, if you try to perturb, the system is totally lost. You cannot more predict the orbits anymore. Unstable. Okay, now I just consider a last example. That is a dipole collision. First, it's better to start with this. You can see here dipoles of different sides, they are colliding. Some angles after the collision. Pattern of two dipoles of different sides. Let me try to explain you. This is just the moment of the scattering. You have two dipoles. Here you have equal side dipoles, but they start in some angle, related to the x. Then after the collision, they exchange partners. Then you produce a small dipole and a big one that move on in opposite direction. That you can consider conservation of energy and momentum to predict these scattering angles, for example. Do this for very small dipoles. Very small dipoles used to predict the scattering results. Well, I just finished the part of the spherical surface. Now I would like to talk about the last topic, vortex dynamics on general compact surface. Okay, all this that I already explained was a result of this work here. 2 years ago, and already in this work, you already make the end, I already told you that global trap is not spherical. Basically because of this spectration traps produce, and there is a necessity of going further than this. The question that appears is how does the change from spheroidal one affect the dynamic of the vortex dipole? You have to remember that when you go to the spheroidal shapes, don't have uniform Gaussian curvature anymore. And this is the result of a second work that we have. Try to generalize the spherical dynamics. To generalize this, you have to use some form of projection. So also on the method of the thermal coordinate. Okay, let's then start to explain what means thermal coordinate. Start with the metric in a complex plane. You have the here, polar coordinates in the plane. Here you have the lambda as being the scale of overall scale factor. On the other hand, here you have the metric for the right, and in this case is a symmetric compact surface, general one. No need to be an ellipsoidal. Have a beta here is the metric of the surface, the metric parameter. And you already see here that it's not isotropic metric. Our goal is to go from a isothermal one. Have the same coefficient for the variation. Well, how we can then connect these two? Basically, you can see here that you can extract both outside here. And then you have the whole by whole, you can connect with the expression here. That you can get, and the integration gives us the calculating of both theta, basically the integral of the weight of the metric. On the other hand, here you have the lambda whole outside, and you can connect with the metric head over half. Then you have the second relation. Metric in the surface. This is the two that you use to connect the complex into the arbitrary surface, physical surface that you are interested in. Well, this me just show you an example. Start again with a dipole position. Simple. Now in axisymmetric compact surface. Starting with that issue in the plane. This is already the expression of how it will look like when you go to the arbitrary surface. Of course, you have to calculate this expression for whole by using that integral of the metric. Here I just show you an example surface that is called Chinese base surface. And you can see here the dipole, first pole, that one has C minus P over 2, and theta angle is a little bit bigger than P over 2. Vortex, line in white is the isocontour for the place, whereas this black line is the. Then you determine this by solving that integral there, but this is a numerical case. You can easily calculate the base and the arbitrary surface. Okay, now determine this one. Dynamics of the vortex. I'd like to remark here that this transformation to the complex plane introduce additional contribution. And on the physical surface, we have the same for size for all the singularities. But if you go to the complex plane, you see that you have this denormalization of the form by the local scaling factor. As you are considered the vortex J, and then the 4 will be rescaled by this scaling factor over the position of the vortex. And this gives us this new expression for the velocity field that has not just the string function that characterize the influence here, negative vortex, but additional term that is the logarithm of this lambda plus this scale factor in the position of this positive vortex. This correction here comes from that term that is self-flow. When you are taking all this contribution, self-flow depends on the core of the vortex. This is the reason that we have this correction. This is the general expression for the arbitrary number of vortex. Well, I like to talk a little bit deviation from dynamics, but I will think a little bit how you can derivate the dynamic equations for the vortex, but by using the calculation of the total energy of the system. This is the definition of the total energy, the square of the flow of all the vortex. You can take the integral and see that this is the basically expression for the energy. The first term is related to the interaction between the vortex. It will be a result of the cross terms here of the velocity. Whereas the second one originates from the self-energy term. One of the you can use this total energy, make this partial derivative of this, and obtain this canonical Hamiltonian equation, whereas this total energy is the whole of the Hamiltonian, that is the coordinate of the vortex canonical. Very interesting expression. You can see that the total energy of the system is conserved by combining these two. And also have some interesting particularities of the expression that see, like you have a gradient of the energy, look like a force for their vortex. But the force is connected with the velocity of the charged vortex. It's not like the Newtonian dynamics that is for massive particles. Force connected with the rotation. Vortex is a little bit different. Beside that, you have that the force produce a perpendicular movement. Vortex like to go perpendicular to the direction of the force. That is cross between theta with p. What is particularities of the vortex dynamics? Well, finally, I go to my ellipsoid. I catch all my technique and apply to the ellipsoid surface. One of them. This is the metric. The corresponding metric parameters of this is the Gaussian curvature of the ellipsoid. Just to show you that the Gaussian curvature relates to the correction that I showed you before. Curvature correction of the vector that appears the energy. Related to the Gaussian curvature by this formula here, like a Poisson equation, where the Gaussian curvature is the source for this field that is characteristic of this correction. By relate to the curvature, correction of the energy, and then to the velocity. The important point, how this what if it was constant, then you don't have this correction. Okay, just here to finalize, I will show you some example of dynamics in orbit, some symmetric configuration. First, you have here two dipoles equally distant from the equator, that they start to synchronize movement, where you keep the angle theta fixed, and you have the same p for both, same determination. And if you calculate how this transverse velocity depends on this angle theta, remember that theta is the angle that the positive vortex makes in the first pole. Negative one has p minus. You see here that you have this for three different shapes: prolate, void, a sphere, the limit. Now blade one. And you see that if it goes to zero, have both poles, then you have zero movement, where is diverge when they approach each other in the equator. Just mention that this flat region here in the blue curve that call more attention can be related to the energy of the pole configuration in a very elongated system. To know, for example, in a cylindrical surface, that through vortex, energy depends on the distance between two part of the dipole, instead of depending on the logarithm. There is that you have this constant relation far away from the poles, né? The another configuration that you just consider starting the vortex in the equator, also they go together, né? North and then go back, né? Initial point, describe the circular orbits. And here also synchronized, and the chordal distance, né, between both vortex also constant, né, like in the other thing. Now the last example is this more asymmetric configuration. Start here, positive vortex here. This is a graph of theta, radial direction, and phi transverse. And for arbitrary configuration of vortex, we do not have more how to do predictions of the orbits, then we have just the numeric solution. To my last video. Here is the surface of the ellipsoid, the plate. Here is the projection. And this dot here is the position where the vortex gets close to each other. Time there. For the distance, the less possible value, I mark with the okay. Then in this case, quasi-periodic motion, no closed orbits, and the chordal distance is not constant anymore. Né? Despite you still have the energy and angular momentum. Chordal distance not more curved. And here, for this case, I represent in time how the chordal distance change. And below, we have how the modulus of the velocity of each one of the vortex, the positive and negative one, will change. That have the half of the frequency of the distance. Exactly the half. And below, the more important graph is how the Gaussian curvature of the position of each one of these charts will change during the movement. You can see here that you have, when you have a less velocity field, a low velocity field, you have the high curvature. Make us to conclude how the curvature is low down and the vortex. Vision most curvatures have the vortex going. How the curvature. Well, now I'm in my conclusion. Sorry, time. So I try to present you a method to determine the dynamics of single vortex and pairs, general compact surface. The dynamic for a vortex part is in spheroidal surface. Also, negative double graph. I thought to show you how this evolves. Also, it's an important point that the low energy cost of the vortex imposing these thin shells is less than if you are considered a traditional harmonic graph. You can expect to have this spontaneous generation of these and more easily seen the experiment. Some of the topics that I still working on, the evolution of these dynamics, now consider the dipolar condensate in the shells. That gives me some inhomogeneities in the density field with the superfluid. Try to characterize how the inhomogeneities modify the vortex. This is also important for to characterize the real experiments that we have this problem. And also to explore non-trivial compact geometries in spheroids. Things for the future. Okay, I would like to thank then my group. Here I represent the group in the physics of some cards. Here I was receiving the visit of Professor Fax. Have some students, master students, Marino, Helena Machado, that are participating in the workshop. Also our postdoc Lucas Madeira, all there. I'd like to thank Professor Banhato that come to us with this idea to explore the properties of the superfluids and the shapes. Also, I'd like to thank you. Thank you very much for your attention.
Yeah, and thank you very much, Monica, for the great talk. I'm sure there are questions. Who wants to start?
I have an experimentalist question. So, Monica, the sphere is very beautiful, but have you thought about a cylinder, a cylindrical shell? That has the experimental advantage that you can use Gaussian Laguerre beams to construct it very easily.
Yes, I noticed the cylindrical shape. I studied this the prolate one, and you can, for example, consider you are very elongated, you are very far away from the poles. You can consider more or less that the physics is similar to the superfluid in a cylindrical film, superfluid dynamic of vortex in the case of a cylindrical film, but just far away from the poles. This is the question, sorry? I'm not hearing you.
I'm sorry, can you hear me now?
Oh, no, yes. Now I can.
So I'm talking about a cylindrical shell. So a real cylinder, not an ellipsoid. So the boundary conditions would be different.
Oh, yes, yes. But I've not explored the cylindrical, just the cylindrical limit that was when you are very far away from the poles of this prolate shell.
Mm-hmm. Okay.
But I think it's possible to produce these cylindrical films.
Monica, thank you so much for this interesting talk. I understand that you did the calculation so far with the point vortex model. Once we do this with the Gross-Pitayevsky equation, for example, for this dipole dynamics, do you expect much difference in respect, for example, regarding any annihilation of vortex, anti-vortexes in this kind of geometries, for the fact that your reservoir of phonons now is not a continuum, so you probably don't really have the same kind of physics, right? For example, imagine that you have a dipole with certain energy that can decay via some Fermi golden rule argument to continuums of phonons. Now your phonons are discretized. What are your perspectives and what is your intuition for this kind of problem? Thank you.
So in this case, you have many differences. If you consider the full Gross-Pitayevsky, you have the effect of the core, the dynamics, and also the production of the phonon that you said. I expect that you have many different behavior, even when you have the collision of the vortex, produce phonons, and phonons can interfere afterwards in the vortex dynamics. But I don't know how to do the system of this dipole, that you have to do all the simulation. Or, in this case, you always have the uniform system, and the core is not a problem for us. It's always constant, the surface. But all the question of phonons, that will be very taking will be very effective for the vortex dynamics. We have many experiments that show how this affects. Effective, very relevant for us.
Next question.
Hi, Monica. Maybe I should have asked you before, but the dynamic is very nice for these point vortices. And the first question, how fluctuations can change all this? Those trajectories you show will still persist under small fluctuations because you are living in a perfect world for the superfluid. Second question, vortices are not a point. They have a core. And is that make any difference when they collide?
Yes, Well, as I told you before about the core, in this case they will be constant. Then the problem when the vortex is very the problem when they're very close to other, then have some problems. Cannot treat point vortex when they are very close to each other. Problematic in this sense. And about the fluctuations, if you consider them neat temperature system, have to deal with this fluctuation. Have to consider the thermocloud there, and even the model we try to justify it will produce these vortex in these geometries in a finite temperature system. For example, try to cooling down the system, and during the production of condensate, it can appear these vortex pairs there. Then, of course, the fluctuation will be very important for consider for real model. About the collision of point vortex, if the chemical potential is high enough, you can consider even the collision is not so different scenario that we showed here. If you have a high enough chemical potential. Otherwise, for example, when we consider non-uniform density, which is high, and now we have to look for the core changing with the position of the vortex, and vortex, or affect even more this collision.
So I think after Wanderlei has pointed towards next papers which may follow, I think it's time to stop and to thank Monica for the great talk and the discussion. I think we have now a break, if I'm not mistaken, for about 20 minutes.
system. And by saying quantum simulation, some implications of that is that the system itself of cold atoms is not in and of itself a quantum many-body system, but it is. But it may or may not model a particular material depending on how well we do in setting up the Hamiltonian to represent that material. So quantum simulation means that we're going to use, in our particular implementation of it, that we'll use ultra-cold atoms, fermions, as stand-ins for the electrons in a real material, in some electronic material. And then we can tailor the potential that this electronic material is operating in by changing optical potentials. So you can make optical lattices, for example, or you can make optical tweezers. There's various implementations of these kinds of optical potentials that, that mimic a real solid. Okay, so I'm going to give two examples actually of quantum simulation, but rather focus on the second one, which is spin charge separation, which is a 1D effect. And the people in blue, I'd like to acknowledge, and I'll acknowledge them again with their picture at the end. Ruin Senarate is a research scientist in my group. Daniel Cavazos is was recently a graduate student. He's now graduated. Yateng Chong is working in a quantum computing company. Ashish Kafli is still in the lab, and Sunglin Yang is working for Google. Boo. And the people in red are theoretical colleagues, Yiwen Guan and his group, as well as Han Pu, my colleague at Rice University, which this is a picture of. All right, so let's go ahead and begin. So the value of cold atoms and optical potentials for quantum simulation really derives from the fact that they're so flexible in that their parameters can be adjusted and tuned, and also the systems are extremely clean. So whatever we make, we know we've made it. So there are no unknowns, impurities, and defects to the lattice that would be a detriment to what we're trying to model. So this ability to tune the parameters is given here in really a subset of the kinds of things that you can vary in these experiments. The interaction strength, lattice parameters, temperature, geometry, various kinds of spin-orbit interactions, even disorder. So if you want to model disorder, in some of these many-body localization experiments do involve disorder, you can actually put that into the system by, for example, optical speckle. All right, so whoops, let me say some examples on the right-hand side here. So the examples that I'm going to be talking about are quantum magnetism, the first experiment that I'll discuss, and then also strongly interacting 1D systems, which you can make by using an optical lattice. So an optical lattice is nothing more than just standing wave of light, and in this particular case, you have one standing beam, one standing wave, and that standing wave produces a one-dimensional array of two-dimensional pancakes. And those pancakes can interact with each other. There can be tunnel coupling between them, or they can be completely independent two-dimensional systems. The same is true at the middle optical lattice. This is a two-dimensional optical lattice that produces a two-dimensional array of 1D tubes. And those 1D tubes can be in exactly the same way as the 1D lattice. Those tubes can be completely isolated, so you have an array of isolated one-dimensional systems. All right, so this is a diagram of the ground state of lithium-6. So lithium-6 is a alkali metal atom, of course. It has two stable isotopes, lithium-6 is a fermion, lithium-7, by virtue of the fact that it has one more additional fermion, an additional neutron, is in of itself a boson. So we're going to be looking at lithium-6 today, and this is what the states look like, how they evolve as a function of magnetic field. And that's relevant to us because we're going to use Feshbach resonances. And I'll assume that you've heard a little bit about Feshbach resonances already. And the Feshbach resonance give us a way of tuning the S-wave interaction strength by varying magnetic field. So these two lowest going hyperfine sublevels, the corresponding to different nuclear spin projections, are pseudo-spin a half system. So we need two distinct spin states. Those two distinct spin states are these two hyperfine sublevels that I'll call up and down. And they're not really up or down, but they're just some up and down in a pseudo-spin, a pseudo-spin idea. So this is what the S-wave interactions look like. They interact with a two-body potential, and the two-body potential is usually, this is two S states interacting with each other, colliding in their electronic ground state. And that interaction potential is a van der Waals interaction. It goes like 1/r⁶. So that van der Waals interaction is relatively short range, of order a nanometer or so, which in comparison to the de Broglie wavelength at these ultra cold temperatures, microkelvin temperatures, this is really, really tiny, about a factor of 1,000 less than the de Broglie wavelength. So what that means is that the details of this potential don't really matter in a collision. And what really matters is the scattering phase shift, or equivalently, the S-wave scattering length A. So I'll refer to A here several times throughout this talk. It comes from this kind of a picture where there's a scattering phase shift, which is that scattering length goes to a constant at low enough temperatures. All right, so here's a little outline of what I'm going to be talking about. The first experiment was done a few years ago now, so I'm not going to spend a lot of time on that. But we studied the Fermi-Hubbard model, and I'll describe what the Hubbard model is in a moment. And its attributes in the region that we were studying are this compressibility. It has a mod insulating state. It's an insulator because of interaction. It's an interaction-driven insulator. And that's depicted over here in this picture where the spins are randomly oriented, but there's exactly one atom per site. And at low enough temperatures, the spin sector also orders, and it orders in such a way as to produce antiferromagnetism, which is depicted in a cartoon-like way here. And then in more detail, I'll talk about strongly interacting fermions in one dimension. So in one dimension, there's some unique attributes to how these systems interact and what their low energy excitation spectrum looks like. And I want to emphasize that. And one of the main implications of these strongly interacting 1D gases is that the spin degree of freedom and the charge degree of freedom separate in terms of their velocities. This is a picture of velocity versus interaction on the lower scale. So I'm going to have to use the other pointer. I think mine's running out of battery. So this is a Hubbard model. So the Hubbard model has long been thought to be a minimal model describing high temperature superconductivity. But we don't know that for sure. But we do know how to write down the Hamiltonian of the Hubbard model. It's defined, has just two terms to it, has an interaction term, in a kinetic energy term. So the kinetic energy is given by tunneling through this periodic potential. It's assumed that atoms live in these lattice sites, and they can tunnel from one site to the next. If the site that they tunnel to is occupied by another atom of the opposite spin state, so the atoms will interact via this large S-wave interaction, and that causes them to avoid double occupancy. So the mod insulating state is driven by the interactions, by the repulsive interactions between the upspins and the downspins. All right, and it's a single band. We're assuming a single band model, so we're going to ignore the possibility of double occupancies on the same spin. I have to get used to my new pointer here. Sorry about that. The back. There we go. All right. So this is the Hubbard model is very interesting to the cold atom community doing these kind of quantum simulation experiments because A, of its significance, the significance of it possibly being a model of high temperature superconductivity would be very exciting to be able to show that. But also because it is a paradigm model of strongly correlated matter. So in a strongly correlated system, every particle interacts with every other. There's no the mean field picture doesn't survive in a strongly correlated medium like this. So it's a very difficult problem to deal with theoretically. And in fact, that's why we don't know the answer to this question about whether the Hubbard model contains ITC within it. It cannot be solved exactly. And the basis size, the number of particles involved in any kind of an excitation scales like 2 to the n. All right, so the mod insulator is the state of what's called half filling, where there's exactly one atom per site. Unit filling would be where you have one upspin and one downspin. And otherwise, this is half filling. And in half filling, the Hubbard model can be represented as a Heisenberg spin model. Dang it. The Heisenberg spin model where there's some exchange coupling J, and then the spin projections Si and Sj. And this J is equal to, it's called the super exchange operator. And it's just simply is the operator that involves an atom or an electron tunneling through a barrier, sampling what's on the other side, and then tunneling back again. So this is a second order perturbation term. And it turns out to be a relatively low energy scale. But for more reasonable scales for us, for the cold atom community, we can make a mod insulator if the temperature is less than the interaction. So T being less than U. So, and with U being sufficiently big compared to the tunneling. So that's a mod insulator. And it is a strongly correlated many-body system. So it's been very interesting over the last 5 or 10 years to be able to have the opportunity to work on this system. So this is a little bit more complicated picture. This is the average number of particles as a function of chemical potential. And chemical potential is a proxy for density, really. So when the density becomes equal to that of a half-filled lattice, then this Mott gap develops. There's an energy gap. This is an energy scale. There's an energy gap that gaps out excitations and causes it to be an insulator. So in this regime, in this Mott insulating regime, there's a random spin orientation, but exactly one atom per site. And this really, the mod insulator, the Bose mod insulator, really set off this field when Emmanuel Bloch and Marcus Greiner, or excuse me, Emmanuel Bloch and collaborator at that time, Marcus Greiner, and Tillman Esslinger and ETH, both obtained evidence of double occupancy, suppression of double occupancy, and boy, I just lost my train of thought. The compressibility is the other measure that one can use to show that you've obtained an insulator. All right, so these are those people who did that experiment back in 2008, suppression of doublons, and in Bloch's group, the incompressibility. So in the special case where n is equal to 1 and you're at half filling, that Hamiltonian, which was so daunting, now becomes just a simple Heisenberg model. And the Heisenberg model can be solved exactly. So this can be solved in the regime of the mod insulator, where you have exactly one atom per site. And I mentioned again J, the super exchange operator. And if the temperature is below that energy scale, the temperature is below the Néel transition, it will transform into a magnetically ordered antiferromagnet that looks something like this. And this temperature is quite low. It corresponds in entropy to having exactly log 2 kb of entropy per site. And at that point, when you go below that, then the spin degree of freedom really begins to freeze out into this antiferromagnetic structure because of the sign of J. Okay, so getting the temperatures low enough to be able to approach this regime has been challenging, and to say the least. And none of the groups that have been in this business have gotten very far below the Néel transition temperature. So let me show you what our results were. So this is the compressibility measurements that shows that when you get to low enough temperature below U, not below the super exchange, but below U, then you can suppress the ability of the gas to change its density. So in fact, if we just look at this frame over here, this is a picture of distance along the lattice from the center of the lattice outwards. And this is the density in units of atoms per lattice site. And you can see if the temperature is relatively high and or relatively low, but the interaction strength is low, then there's just kind of a more what you'd expect, Gaussian looking or very smooth looking function of density as a function of radius. But if these are the so-called Mott plateaus. So if you go out to higher energy, higher repulsive energy, then as I mentioned, you get an interaction-driven insulator shown in blue and red for temperatures corresponding to either 11 or 14 units of hopping below which gives us a strong enough U over T to be able to make this mod insulator. So that's a mod insulator. This is approaching a band insulator for those of you who know about that kind of thing. The band insulator would just be, in this case, 2 atoms per site. And eventually, with low enough interactions, this would look like a band insulator. So the theory was done by Ehsan Khatami, who's at San Jose State University. And Ehsan did something called the numerical length cluster expansion, for those of you who are in the know on this kind of stuff. And you could see that they got these compressibility measurements right on. I think there's only one adjustable parameter. Okay, now to show the antiferromagnetic order, we use Bragg scattering of light. So this is really equivalent to what the solid state people do, where they scatter neutrons off of a lattice of polarized electrons or magnetic electrons to be able to see magnetic phases. So this is completely analogous to that, except we're not using neutrons or X-rays to scatter, but we're using optical light, visible light, in this case red. So light comes in at a particular angle called the Bragg angle, which is along the 111 direction with this three-dimensional cube, three-dimensional lattice, and it will scatter light coherently if this angle is chosen properly, so that that coherent scattering transfers exactly 1 unit of angular momentum along the 111 direction of the lattice. Now, in some other different direction, not a specific direction, you send in light at the Bragg angle, you get only incoherently scattered light everywhere else except for this one other direction that satisfies the Bragg condition. So this was an experiment that was done in my lab with Russ Hart and Pedro Duarte. Pedro is from Colombia and a very gifted experimentalist, and they together did these experiments. So you can see as a function of U over T, as we adjust interaction strength, and we lower the temperature as much as we possibly could. So we did everything that we could to be able to do evaporative cooling, which is the really the workhorse in these experiments, is in order to get temperatures below the Néel transition. Well, we got temperatures low enough that we could see this magnetic ordering. So this is the so-called structure factor, which is the fraction of this light which is scattered coherently. And the structure factor indicates kind of how many sites of correlation that you have in your system. And you can see we have of order 2 sites or so, which are correlated antiferromagnetically, which means that if I look somewhere over in here, compared this atom probability to be up compared to its correlation with this one being down, there'd be very little correlation. So it turns out that we're not above the Néel transition, but we were really close to it and just above it. So if you look at again, Ehsan Katami and some others who did quantum Monte Carlo calculations, these are the different colors corresponding to different temperatures in the lattice, and along this axis is interaction strength, where for a variety of reasons, the antiferromagnetic ordering favors being somewhere around U over T of about 10. And you can see that our data fits pretty well to this green curve pretty consistently. And this is the data that's at the pi direction, which is the Bragg angle. And this is Q is theta. It's just some random direction. And you can see in the random direction, there's no correlation. Everything is completely flat. So this temperature that we could fit in this way was actually very precise. As you can see from the temperatures that are given over here, each of those colors correspond to just a few % difference in temperature, and they have great sensitivity to this height of this peak. So the height of that peak is really telling us where the antiferromagnetic ordering is largest. Turns out to be right around in here. If we could go to lower temperatures, this peak would increase exponentially as we went below the Néel transition. All right, so this just summarizes that. We're able to get to about 40% above the nail transition, and which was better than anybody had done at the time in 3D optical lattices. This is Tillman Esslinger's group, and but since then there have been 2D experiments, these quantum gas microscope experiments. They do single site resolution. They're really beautiful and very sensitive, and they're able to show that they can get below the nail transition. This is Greiner and Bacher, Zierlein, and Christian Gross, and in Munich. Let me make sure I get the button correct here. All right. Okay, so that is the story that I'd like to tell about the Hubbard model, which is really a paradigm model of the experiments, the kind of experiments that we can do with ultra cold atoms. Now, I'll give you another in which the precision was a lot better, in the sense that we were able to distinctly see the spin charge separation between the spin wave velocities and the charge wave and the spin wave velocities of sound. Okay, so in 3D, particles can avoid each other. 3D is very different than 1D in this regard. In 3D, particles can avoid one another, go around. There might be an interaction with one or two, but not everyone. And so typically three-dimensional systems are not strongly correlated, and their excitations are quasi-particle-like and fermionic. They're given by fermionic operators. So this Landau-Fermi liquid theory, which has been very successful in describing these three-dimensional systems, developed quite a long time ago now, is essentially a mean field theory. Now, in the other case, in a 1D system, everything's strongly correlated, because any particle which interacts with another is going to knock with its neighbor, then interact with that neighbor, and so on. So all of the particles, the electrons or atoms that are in this one-dimensional tube are going to strongly interact with one another. That means every excitation is a collective excitation. Every excitation is collective in 1D. And so the excitations turn out to be sound-like, meaning that they disperse linearly, and they're given by bosonic operators, and was described first by Tominaga and Lettinger in a theory which is now called the Tominaga-Lettinger liquid theory. In the Tominaga-Lettinger liquid theory, the prime prediction that they have is the separation of velocities between spin and charge. So let's see how that works. So in 3D, the excitation spectrum, this is energy versus momentum. Anything that happens at the Fermi surface, as long as the momentum transfer is less than 2 kF, there's a way of doing it, connecting a spot on the Fermi surface here to here, that's 2 kF, or from here to there, that's almost 0. So this is the case in 3D, where the excitation spectrum can be satisfied for all of these momenta. So for 1D, it's completely different. Instead of having a spherical Fermi sphere, Fermi surface, there are Fermi points. So there's one here on the left and one here on the right, and those are the only indicators of what the Fermi energy is. So the Fermi energy spans, these two Fermi points span 2 kF, just like here, but you can't go around in an interaction, go around your neighbors. So consequently, the excitation spectrum looks like this. So this is energy versus momentum again. This is about Q equals 0. This is an expansion of about Q is equal to 2 kF. And the excitation spectrum, the low energy part of it, the high energy is the same, but the low energy part is very, very different in the three-dimensional case. And this just shows that mathematically. This is actually comes from Thierry Giamarchi's book on quantum physics in one dimension. And this shows the case where momentum transfer is equal to 0. And this is the case where the momentum transfer from across the Fermi points is equal to 2kF. So these excitations are sound-like for small q because they have a dispersion relation which is linear in momentum. So the energy is linear with respect to momentum transferred. And VF is the Fermi momentum. So this is what the excitations look like. There's a long chain of particles which are have antiferromagnetic correlations in their ground state. And you can excite either two adjacent atoms that are same or different spin state, and that creates a charge excitation, sometimes called a holon. And that charge excitation then propagates down this one-dimensional tube at some particular velocity. Now, in the case of the spin-on or the spin degree of freedom, it's a very similar idea, except now you're exchanging two spins. You're exchanging this spin for this one and this for this one, and they change position, creating this defect. And that defect is known as the spin-on, and it propagates down this one-dimensional wire as well. So for a homogeneous density and small interactions for the charge degree of freedom, you can do perturbation theory, and you see that there's something which depends on interaction strength called the Lieb-Liniger parameter. Depends on that scattering length that I started out talking about. And that scattering length is linearly dependent on gamma in this equation. So this is for the charge degree of freedom. For the spin degree of freedom, there's a minus sign here. So as you increase interaction strength, these excitations grow more slowly. And these excitation velocities increase with interaction. And that's shown here. So here's the dispersion relation for low energy. You have two different slopes of omega with K, and those two different slopes correspond to the two different modes, the charge mode and the spin mode. So those charge degree of freedom and the spin degree of freedom are completely independent of one another. And it turns out that it's possible to excite one and not the other independently. And so that's a interesting challenge for an experimentalist, because if it's possible to do, then you should be able to do it. So how does that work? So in the case of electrons, and work that was done over the last 20, 25 years, people have seen spin charge separation in various quasi-1D-like systems. This is a case of ARPES, where you can see, I think, quite beautifully the difference between the holon and the spin-on in terms of their dispersion relation. There's also been experiments with cold atoms. And this particular one was a thesis experiment of my colleague Guido Pagano while he was at the University of Florence. And Guido did an experiment with, I can't remember if it's dysprosium or it's a high spin atom that has no Feshbach resonance. There it is, ytterbium. Has no Feshbach resonances, so you can't adjust interaction, but you can adjust the density by including these various synthetic dimensions, they're called. So he could measure this using something called Bragg spectroscopy, not Bragg scattering. And I'll describe in a moment how Bragg spectroscopy works. But that gives you the correlations in the system, the spin-spin or the charge-charge correlations in something called the dynamic structure factor. All right. So this is an experiment more recently done by Christian Gross and Emmanuel Bloch. And they they had this two-dimensional array of individual atoms that they could individually access and image. And these atoms, by removing one in what's called a deconfinement transition, they blast away very, very surgically just one atom, which blows off this otherwise filled lattice. And that creates spin and charge density waves that propagate away, and they propagate at different speeds. The issue about this experiment from the sake of comparing with linear liquid theory is that this deconfinement transition is an explosion, and it's not a low energy excitation. It's a relatively high energy excitation. All right, so we set out to be able to study this effect, and we use, of course, an optical lattice to make a bundle of 1D tubes that I mentioned to you earlier. And then we use this technique, this measurement technique that's known as Bragg spectroscopy. So Bragg spectroscopy, you make a grating by having two lasers that are at some small angle with respect to each other. And that angle means that the decomposes into a momentum transfer along the tube axis. So this is Q, which is the difference between K1 and K2, and omega is the difference between omega 1 and omega 2. So you can impart a fixed momentum, and you can vary the energy of this energy difference between these two beams. And if you can measure a response to that somehow, and people have done Bragg spectroscopy with fermions before, including, as I mentioned to you, in Florence, but also at ANU and Swinburne, or at Swinburne University in Australia. Trying to see how much time I have. Maybe Axel can tell me, or Nate. 10 minutes, okay. We can do it.
10 minutes for 1 hour. And then
Okay,
yeah.
I'll get it done. So
Yeah.
thank you. So so it turned out that we could measure the charge density wave very readily by detuning large distances between these two states, which correspond to our upspin and our downspin. But when it came to measuring the spin density wave excitation, which is excited by symmetrically, this is a little rather technical right here, but exciting in a symmetric, anti-symmetric way, the light shifts between the spin down state and the spin up state allows you to access the spin density wave, whereas this is a symmetric excitation. So this is what I was saying earlier, that it's possible to find a way to excite them independently, so we can excite in one experiment this wave and another experiment the other wave, and that enables you to really isolate and quantitatively measure their speed. So for those of you who are interested in optical lattices, this is just some technical details about the filling factors and the tunneling and the temperature. All right, so this is how what Bragg spectroscopy looks like. We take an image without a Bragg pulse, and this is an absorption image of the entire cloud in which the tube axis is moving is horizontal here. And this is the case where we've introduced the Bragg beam, and you notice there's a little bit of a region here of the distribution which is cut away. So if you take the difference between these two images, this one with Bragg pulse, this one without, then you find that you have this outcoupled group of atoms whose size tells you how big that correlation was that gives you the dynamic structure factor. So that red area corresponds to that little peak right there. So by measuring the size of that little red peak, that gives us the structure factor and the speed of sound. So this is a little bit of theoretical work in which the output momentum transfer is related to the dynamic structure factor, which is in turn related to the temperature in this way. And in our case, beta, the h bar omega compared to the temperature was about 20%. Okay, so that's Bragg spectroscopy. So I mentioned to you that the spin density wave has proven to be much more difficult. The separation between those two spin states is 70 megahertz, and the line width of the transition is only 8 megahertz. And so you're very close to both of those states, and they spontaneously scatter, and you're looking just for coherent scattering. So it completely destroys the signal that you have and doesn't work. So we had to find a workaround to do that spin part. So we did the charge part right away, and we did the charge part using the regular 2s ground state of lithium-6 that I started off showing early on, these two red levels, and driving with red light that's far detuned, this is about 10 gigahertz. We're able to couple the Bragg spectrum to this transition. So there's an upward going laser beam, and another one takes it back down again. So that worked great because we could make this detuning huge. This detuning is not huge, and it wasn't working great. So what we did to improve it was to use not the 2s to 2p transition, but rather the 2s to 3p transition, which is about 10 times narrower than the red. This line width of 2p is, I think, 6 megahertz, and this one's 800 kilohertz. And we also used the third level rather than the bottom two. We used the bottom and the top, the first and the third, and that increased the splitting between these two levels. All right, and that worked. So we were able to do this experiment with separately exciting the spin wave and the charge wave and avoiding all the spontaneous emission, all the heating from that. So what's shown on the left is the actual data for both the spin mode and the bottom in blue. Spin mode is always going to be in blue, and the charge mode here in red. And the lines are theory from Jiwen Guan's group in Wuhan, China. And you can see the agreement's pretty good, but not perfect, especially here in the spin mode. The spin density wave, there are some definite discrepancies. So what's going on with that? So it turns out that there are nonlinearities in this system because the momentum transfer is not much less than KF. It's a factor of 5 less than KF. And that gives a little bit of an effect. And I'll discuss that in the next slide. But here are the results, assuming that linear theory worked. And to the most part, it did work pretty well. And you can see that the spin density wave is getting slower with increasing intensity interaction, and the charge density wave is getting faster. So you're faced with this very weird scenario where you've got these electrons in which their spin is moving more slowly than the charge, and the charge is moving away from the spin. So physically, they're delocalized from one another. So it's one of the weird things about quantum mechanics, and manifests itself here in a very dramatic and beautiful way, I think. All right, so there is this nonlinear scattering that's contributing, and you can see that in the width of the spin mode. This is the outcoupled atoms that I showed before, and there's some width along the tube axis after some short time of flight that doesn't show up with in the charge data. So you can see that here. This is a plot of the width of that outcoupled, that red portion, outcoupled fraction of atoms. That's the width in some spatial measurement. It's arbitrary units, actually. Doesn't really matter what that is. But you can see that for the charge mode, this is relatively flat. In the spin mode, it's increasing. Uh-oh. I'm done, I guess. So let me flash it up here. So this is, it turns out that the dominant nonlinearity is the band curvature, which I showed earlier. For the charge mode, it goes like Q squared. But for the spin mode, it's different. And this was something that Ji Wen discovered in the context of looking at this data, was that this nonlinearity is called backscattering. It's a two-spin process, and it requires two different spins scattering from each Fermi point. So this one and this one, and they reach across the Fermi points, and they accounted for that. They calculated it. So the extremely difficult calculation, I understand. But now you can see the solid line is after counting for nonlinearities, and the solid line is in almost right on, almost perfect agreement with only one free parameter, which is the temperature and the overall scaling. So it's 1.5 free parameters. So you can see it's particularly for the spin mode, there's a big improvement between what it was and what it is with the nonlinearity. All right, so it turns out I'm not going to tell this story because it would take me a little bit more time. But more recently, we've been studying a spin incoherent Schrödinger liquid, in which the spin charge separation is disrupted by thermal excitation. Okay. So skip by that. This is one of our key experiments, is to try to make a P wave superfluid. Nobody's ever seen a P wave superfluid, or except for liquid helium-3, I should say never. But the only liquid helium-3 is the only P wave superconductor that's known definitively. And also in cold atoms, we've not made P wave superfluids either, and we're working on that, mainly because of the possibility of seeing Majorana fermions at the ends of these wires. Okay. So let me acknowledge the people who did the work. Particularly Ruin and Danielle, and the rest of these people are on various other experiments. Ashish is a relatively new graduate student, and the others are working on some boson experiments. This is Ricardo Espinoza, who's from Chile, and any graduate student or undergrad who's in the audience who's thinking about going to graduate school and likes maybe attracted to this and wants to look into this, I hope you'll give either Vanderlei a call or me. And we were very happy to have Latin American students who are very well trained to come to our university. So that's it. Thank you.
Thank you. So when you showed the plot where you had the spin and charge velocities over the S-wave scattering, I think. Can you show that plot,
Yeah,
please,
okay.
again?
Let me, you have to tell me where to stop.
Yes, here.
Okay.
No, yeah. So I think up to 100 Bohr radii or so, both
Yeah.
are the same,
Yeah,
and then there's a difference.
yeah.
How does it happen at
Yeah, good question, Axel. So, you know, clearly there's something which is funny about what's going on right in here, both in the theory and in the experiment, because it becomes non-monotonic. You know, if we look here at the charge density wave, it hits a minimum and then it comes back up. The reason for that is that as a function of interaction strength, the density in the tube, the peak density changes. The total number doesn't change, but because the interactions are stronger, that tends to make the density, the peak density, to be reduced. And so we compensate for that using a Bluetooth light that it applies a repulsive optical potential that compensates for the interaction effect of the interaction on the density. So that's that. And it turns out that, you know, down here it works very well. Up in here, there's very little shift anyway. You can see that going from 0 to 100 is really tiny. And it took a lot of time for the students to be able to collect even that much data. Yeah, good question. Thanks.
I think we have time for maybe one short question. Okay, let us thank our speaker again.
Thank you.
what we will be doing here. This is not working anymore. Okay. Okay. So I was saying this cartoon here shows what we are studying. We have a ideal Fermi gas polarized in one of the directions, and we put a down spin in this bath. Eventually, we will put two ions in this bath, but most of our results will be for just a single ion in the down spin state. So this ion will attract the atoms in the bath, and they will form what is called a quasi-particle, a Fermi polaron in this contest. Okay. And so this work is done in collaboration with Renato Pessoa from the University of Federal de Goiás and Luis Ardila, who is at Leibniz University in Germany. My talk follows a pretty standard outline. I will talk about the motivation for this work. I will spend some words in the polarization potential that has some special features. Then I will talk about the model and methods, results, and some conclusions. Well, mobile ions in a Fermi gases can shed light to several many-body systems. These studies are interested in a range of applications that ranges from developing new materials, investigation of fundamental physics questions, enhancing our understanding of quantum matter, and also benchmarking ladder approximations. I will show here preliminary results that we have. Among these results, I mentioned the polaron energies, effective mass, quasi-particle residue, interaction energy between two polarons. This is the only part where we have two ions in this bath. The long-range atom-ion interaction is given by this, is given by R to the fourth, although this is typically I like the expression. Anyway, this is usually we don't need to consider a potential like this, but in this case, it's important. In 1 minute, I will tell you why it's important to consider this long-range tail of the polarization potential. C4 is a constant depending on the polarizability of the atoms, and E is an elementary electronic charge. This potential is true when we go into the limit of large distance separations. It's useful to have interaction characteristic length scale and energy scale. To get these values, balance the asymptotic regime of the potential energy and the kinetic energy. And then you get this R star, which is the length scale. It's associated to the interaction range and determines typical values of the scattering length. On the other hand, we have the energy scale, which is the height of this centrifugal barrier for L equals 1. This is the maximum energy where we have just S-wave scattering. This interaction cannot be neglected. Why we cannot neglect this interaction? Because the characteristic length scale is about another, well, this is just an information. It's an order of magnitude larger than 1 for neutron atoms. The length scale can become comparable to the interparticle distances. Enough in this case, an effective potential cannot be used to replace the polarization potential, despite, in principle, its short-range nature. Usually, long-range potentials are Coulomb potentials, not R⁴, but because the range of the potential is typically equal to the interparticle separation, we need to take into account this polarization potential. At short distance, the electronic cloud of the ion and the atoms repel each other. This potential becomes repulsive about in distance less than 10 Bohr radii. Electrostatic forces cannot describe this type of interaction. These potential at short distance are very intricate. Generally, they are not well known. So, in the calculations, people usually assume some kind of regularization for the potential. This particular one here is very convenient because for numerical calculations, because it has a finite value for R equal 0 or R going to 0. And the parameters B and C are chosen to describe the low energy physical properties of the system. Anyway, when R goes to 0, in the limit R going to 0, this C4 over B4, it's enough to avoid the overlap between the atom and the ions. In the other limit, when R goes to infinity, we recover the polarization potential. The parameter C sets the distance where the interaction becomes repulsive, and the B parameter significantly affects the energy levels that we have. As you can show, as I can show you here, as this B parameter gets smaller, the potential gets deep. Here, this is for the pure polarization potential, and these are the values of this regularized potential of this form here. What we do, we have some latitude to choose B and C. The important thing is to have this parameter in such a way that the low energy process for the highest bound state be taken into account in a reasonable way. And differences of this, when we change this pair of parameters, at small distances can be neglected. We choose in this work this parameter C, which is much smaller than the interparticle distance at typical densities of where we do our calculations and hopefully some experiments. What we do is to keep C fixed and change the value of B. So what we are doing, we are tuning the depth of this regularized potential. To determine the scattering length for S wave, what we do is to solve the Schrödinger equation for zero energy. And what we do is to solve iteratively for B, we give one value of B and then solve the equation. And from the radial function, we get the scattering length. Oops. The scattering length here. And these are what we get. This is the scattering length. This is the value of B in these units. Just remember, as B gets smaller, the potential gets more deep. We have some resonances here. One for this point here, the second one here, and so on. There is also this Buckingham potential, polarized potential. This Buckingham polarized potential is the one where the regularization is just given by this part. In other words, where this prefactor of our potential can be approximate taken as 1. In this case, Schrödinger equation can be solved analytically, and also the scattering length can be known analytically. And in this case here, I show you the results for this expression here by this dashed blue line. The agreement is remarkable, at least in the range of these B values that are for interest for us. The number of resonances that we have here can be found through this expression here. And the numerical values that we have for the resonance is 0.58 R star, the second one for 0.26 R star. And variations of this parameter B tunes the energy of the bound state, mimicking experiments where Feshbach resonances have been observed. The model that we use to describe this system is given by this Hamiltonian, where the first term here is the kinetic energy of the atoms. This one here is the kinetic energy for the ion, and V is the interacting potential. M is the mass, and short-range interactions among the atoms in the bath are neglected, since we are assuming that they form an ideal Fermi gas, a degenerate Fermi gas. The wave function that we use to model the system is given by this expression here. R is the space points of all atoms there, for the ion and the atoms in the bath. F is a factor of the Jastrow form that I will say a few words more in the next slide. And D up and D down are slate determinants. Of course, when we have just one single ion, one single atom with down spin, we don't need this determinant for the in this case. The single particles orbitals in these determinants are plane waves where we take these K vectors in a consistent manner with the side of our simulation box. Okay. How we choose this factor of the Jastrow form? What we do is using this lowest order constraint variational method, which means to solve this equation, this Schrödinger-like equation. And we look for lambda such that the wave function, this Jastrow factor, ensures the continuity of the wave function at a given range. And this range is chosen in a way that minimizes this energy of this equation. Okay, I hope I will not bore you with a few words about our method, but I will say a few words about the variational Monte Carlo. The variational Monte Carlo method, we are evaluating this integral here, where the variational, this integral here can be recast in this form where we have a probability that we sample, and this estimator here, which we call local energy estimator. And what we do is to sample configurations from this probability distribution, and by taking the average of the local energy estimator for a large enough number of samples, this will converge for the trial energy. In other words, the variational Monte Carlo method is exactly the variational method that we all know. What is done is to solve this integral by a stochastic method. This is what is done. Our results are obtained through the diffusion Monte Carlo method. The diffusion Monte Carlo method is one of the projective methods. In few words, what we do is initially is to shift the energy of the Hamiltonian by a constant that I'm calling E here. And then the system ground state, it's obtained by applying the imaginary time evolution operator to a trial state. And here, if I expand this in eigenfunctions of the Hamiltonian, of the energy, I can write this expression here in this way. So if I apply this operator for long enough time, at one point I finish with some with configurations sampled from the ground state. In this constant that we shift the Hamiltonian is more like a normalization factor for these configurations here. Of course, we don't know exactly what E0 is. This is something that we might change during the simulation. Technically, it's important to perform this important functions transformation. This will make our simulations to converge faster and more efficiently. Essentially, what is done is to multiply Schrödinger equation by a trial function that in this context is called a gliding function. The exact ground state is obtained by sampling when we have large enough tau values, the product of the true ground state times the trial wave function. And once we have enough samples from this probability distribution, due to the hermiticity of the Hamiltonian, we are able to apply the Hamiltonian to the trial function and still obtain the ground state energy, the true ground state for the system, just by taking this average here. This will converge to E naught. This is very good for estimating energies. When we go to estimate other quantities, the quantities that do not commute with the Hamiltonian, then we might need to do this, what is called extrapolation. We take twice the result from the diffusion Monte Carlo method and subtract one value from a variational calculation. This is as the variational calculation, as the trial function is better and better, this converges for the exact quantity. Let me talk about the famous sign problem. At least in my area is famous, but because it's ubiquitous in all the quantum Monte Carlo methods. We have this problem when we are trying to compute quantities related to the problems that there is fermions on them. The sign problems arise because of the antisymmetric character of the fermionic wave functions that implies in having very oscillatory functions, very oscillatory integrals. The remedy for this is quite simple, is this fixed node approximation. What is the fixed node approximation? Take a trial function and assume that this the nodal regions of these trial functions are the ones that are the described system. And then why this is work? Because the configuration space is carved up into equivalent nodal regions. And each one of these nodal regions can be reached just by a permutation of the indexes. So if we just keep our calculations in one of these nodal regions, we will get results that are good for the whole system. And as I said before, as the trial function improves, best estimates are obtained. Now let me show you some results that we have. I start by showing you the polaron energy. What is this? This is we put the ion, the downspin particle, in a state with K equals 0, with momentum equals 0, minus the energy of the bath. This is not an easy quantity to be estimated. Why this happens? There is two reasons for this difficulty. One is intrinsic to the Monte Carlo methods. Associated to a Monte Carlo result, there is an statistical uncertainty. So to make a difference between two different results from two different simulations and to be meaningful, we need to have very small variances, which implies in long runs. On the other hand, since here in this problem, we have the long range part of the potential that we cannot neglect, this means that we need a lot of particles there in the bath, which tends to mask the impurity, the results for the impurity. Okay, let's go to the results. First, I want to call attention for this inset here. What this inset is telling us. We have here 1/n, where n is the number of particles in the bath. We want to have this value for the bulk, for a bath in the bulk. So we extrapolate these results, these energies of the polaron as a function 1/n to 0. Each one of these points or the triangles were obtained in this way, doing this kind of extrapolation. The dots are our results, as I said. The dashed lines are results from ladder approximation. And what we see is this. Here I put B/R, but this is related to the depth of the potential. The first resonance happens here just a little bit before 0.6. Up to this point here, the results, our results start to deviate from the ladder approximation. Before reaching this resonance, ladder approximation give results which are in agreement with ours. But the big difference starts when we are approaching the second resonance. Why this is happening? This is happening because after the first resonance, we have a binding between the up spin and the down spin. They are bind, but this energy is very small. As we make the potential more deep, this binding grows, and the effect is to modify the many body strong correlations that we have in the system. Here I have also results for a much lower density of the system. Remember, the density, the interparticle separation is the order of L. No? So in this case, ladder approximation performs much better. But in this case, then just the scattering wave, the scattering length of the S wave gives a reasonable description, because the range of the potential is shorter compared to the interparticle separation. Okay, let's go to the effective mass. How we compute this effective mass? Just by fitting results of this equation here, where we put some in the ion has some moment, and we subtract from the zero momentum, the polaron with the zero momentum. What we did was to perform 3 different simulations and make a fit and extract the mass, the effective mass. There is a much better approach made by the Boronat group, where with a single stimulation, you can extract this effective mass. But we did in this way that I described here. And here we have our results. again, what we see is that as we approach the first bound state between the ion and the atom, the effective mass starts to grow. And what this means, as the potential gets deep, atoms are attracted to the impurity and they become larger and larger. And the effective mass grows as the potential gets deep. Maybe this is can be seen more clearly here with where I show you the radial distribution function for different values of B. So we start with the deep potential, which is this dark line here, and then we are going to even shallow and shallow potentials here. So what we see is that around the ion, when we have the deep potential, there is a lot of atoms around this impurity. Another quantity that we compute is the spectral waste or residue of the particle. So an interactive particle, what is interactive particle when we put there? Some of the atoms, we are doing calculations at 0 temperature, but when there is interaction, some of the particles in bath would jump to excited states. In this situation, Midgal theorem states that the momentum distribution near the Fermi surface has a discontinuity, and the residue or spectral waves can be computed by this difference in the momentum distribution. Is slightly less than Fermi momentum minus the slightly higher momentum than the Fermi one. It happens that this momentum distribution for a momentum is slightly higher than Fermi momentum goes to 0 because of the one-body density matrix has this scaling. So we can compute the residue by computing the momentum distribution. And this is made, is quite standard. This is made by computing this average here. What we have here, we have R prime is just the coordinates of the of R. R prime and R differ just because R has also the coordinate that we have just sampled for the ion. And here we give an arbitrary displacement of the for the impurity. And so the momentum distribution can be recovered if we go to this limit here, when R prime of the ion minus the original position goes to infinity. In this quantity can be interpreted as the propagation probability of the polaron in the bath. And here we have our results. Again, these are results for the ladder approximation. And what we see is that as the potential gets deep, the residue gets smaller and smaller, meaning that the wave function of the polaron is quite different from the wave function of a free particle in the bath. Finally, I will show you the interaction energy between two polarons. How do we compute this quantity? We put two ions in the bath, one in the momentum 0 and another one in the first state, different from 0. And then we subtract the energy of one polaron in the with one ion in the K equals 0 and one ion in this in a state equal to 2p over L. Well, and here the explanation is about the same. Here we see that when we reach to the first resonance, nothing much special happens. As the potential gets deep, then this interaction becomes much more stronger. Well, the latter approximation for a Fermi polaron give reliable results in these two situations at ultra low densities of the Fermi gas, which means that finally we are neglecting the polarization there because the particles are so far apart that the range of the potential is smaller than the interparticle separation, or when the atom-ion interaction is very weak. There is room for improvement in this work here. In our wave function, we can put a guiding function. We can use a guiding function with a long-range part take from hydrodynamic theory that will take into account phonons in our system. This will improve our results. Other thing that we can do is to compute more quantities that might give extra information, like the interactions of molecular ions. Molecular ions are those are in this situation where we have the ion in an atom with a strong coupling. We need to compute the bound energy for the atom ion dimer. Finally, also we could compute the radial distribution function for atoms in the bath. At this point, I just want to thank the funding agents and your attention.
Thank you, Silvio.
So thank you very much. I have two questions.
Sure.
The first one is the results you obtained depended always on the choice of a regularization parameter. So the natural question for an experimentalist would emerge if you have a concrete system. How would you determine the corresponding regularization parameter for that system so that you can make a prediction?
Well, as I told you, and also I showed here, what this parameter does, in fact, the two parameters, what they should do is to give a reliable description for the highest bound state that we have, a reasonable description for this. If you change a little bit these parameters, you change what is happening in the short range limit, which is in fact, the system does not care what is happening there. By changing B, we are trying to mimic what people observe in the Feshbach resonances for this ion.
Meaning one could fix them by looking for the Feshbach resonance, for instance. That might be. the suggestion?
Yes. Of course, these parameters say, I didn't enter in these details here, but these parameters usually are taken in accordance with what people have observed in these experiments with alkali atoms. This point, for instance, C, we kept fixed. And this parameter was taken in agreement with the this type of experiment where the potential becomes repulsive.
And the other question is, if I would naively determine all the results from a Hartree-Fock calculation.
Sorry,
If I would use Hartree-Fock as a first estimate, how much better would you be for the polaron energy, for instance?
Well, the community of quantum Monte Carlo methods always claim that we are doing exact results. There is no approximations that we made. Although this fixed node approximation, the name implies that we are doing an approximation. So I would say that we will benchmark your calculations with Hartree-Fock method.
If there's a Feshbach resonance, is there also an Efimov effect?
Sorry?
An Efimov, a Efimov?
Efimov effect, you said. Well, we didn't enter in this three-body question. It's something interesting that we want to see more carefully.
Oh, thank you, Silvio, for the talk. I'm wondering what happens when you cross the resonance and you enter to the formation of the dimer, at least. So you have to take into account also in the tri-wave function that you're using, it appears a new node. You have taken into account that in the...
No,
because I think that could be irrelevant.
Yes, I agree with you. We should have a kind of pair there, a kind of Cooper pair there in the wave function. I agree with you. This is something that we are missing in this calculation here.
Thank you, Silvio, for the very nice talk. Usually when we have potentials with two parameters like you have, you can use one to fix the scattering length as you did. And the second one, usually we fix to the effective range, because if you continue that low energy expansion, that's the next term. Is what you did equivalent to this?
Yes, what we do is exactly this. We keep the position where we start having a repulsive potential, and then we change this B. By changing this B, what we do is to change the depth of the potential. Here you see this is quite sensitive to the value of B, and the range of the potential, which means to change B, is related to the scattering length of the problem.
Mm-hmm. And another question, when you have those divergences close to the appearance of the bound state, what happens if you subtract the energy of the bound state in free space? So this bound state is going to have some energy in free space outside of the bath. And it's,
Yes, this is, I don't know if I understood well your question, but I think that this is what we are doing here. This is exactly what I think you are asking. We have the system with, maybe not with the bound state. When we are here, we don't have any bound state, but we have the impurity in the bath, and we are subtracting this energy, the energy of the bath.
but my question is, you could in principle calculate the energy of just two particles, the bound state of these two particles.
Oh,
outside the
yes,
bath.
yes. This is something that we definitively want to do, to calculate the bound state, the bound state energy of the pair.
Because it's
Atom,
going to do
ion.
something like this, and if you subtract, maybe, I don't know.
Well, just by itself, I think that this will be a relevant quantity, even if we just have this quantity put here, say, around here to show how this bound state, the energy of the bound state changes with the potential depth.
Thank you.
Thank you very much for this nice talk. I have a final question about what would be the extrapolation of this study to the case of multi-ions. Imagine that you have now not only one, but you have many, many ions in your system, and take, for example, the thermodynamical limit of both ions and atoms. Because of this regularization of the potential that you have, at the end of the day, what it seems to me is that you have some sort of finite range potential. Am I correct? So the potential is not short range, not contact, but finite range.
Yes, it's finite.
And because of that, probably you would get some sort of Roton physics, some super solidity emerging in your system. Is it possible to?
We didn't reach that point. Certainly something interesting. We did some calculations for a polaron in a Fermi polaron, but is out just a downspin in the bath is out the charge, is out the polarization potential. And there we were able to extract what you did. Here is much more tricky. I don't know if we will be able to put as much as we want of ions there.
Okay, let us thank our speaker again.
Thank you.
And I think.
No, I just want to tell you that the dinner is tomorrow, not today, because some that arrived late maybe understood that, but the dinner is tomorrow. Okay, we will announce tomorrow morning. We will give more details about that. Okay, thank you very much.